Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 13 on reasoning about rational and radical equations. So, in this unit we saw how to solve rational equations, and in an earlier unit we looked at how to solve equations that involved square roots, also known as radical equations. Today we're going to look at how we can justify some of the steps in solving those equations and also why extraneous roots show up in some of the solutions to both types of equations. Let's jump right into it now and first take a look at some radical equations. Now we've looked at solutions to square root radical equations and rational equations. Sometimes the solutions to these equations introduced extraneous roots that must be rejected. In this lesson we will look to justify the steps in solving these types of equations and understand why extraneous roots are introduced. First, let's review two basic properties of equality. Alright, the addition property. If A equals B and C equals D, then A plus C equals B plus D. The other way around certainly doesn't have to be the case. Now, the addition property of equality probably seems pretty obvious, and it basically gives you license or permission to add the same thing to both sides of an equation and also actually to subtract the same thing from both sides of the equation, because we just think about that as adding an opposite. The multiplication property is very similar. If A equals B and C equals D, then A times C equals B times D. Again, like the addition property, what the multiplication property of equality basically says is we can multiply the same thing on both sides of the equation, right? And it also applies to division, which basically is the same as multiplication, right? If you're dividing by 2 on both sides of the equation, it's equivalent to multiplying by 1/2. All right. Now, we can use these properties to justify certain steps in solving both equations that involve square roots and equations that involve fractions. Let's take a look at exercise number 1. Give a reason or cite a property for each of the following lines in the solution of the square root equation x equals the square root of x plus 6. Now, I do want to point out there's quite a few steps in this equation that we don't particularly justify. I just want you to look at the ones that have got the lines beside them. Obviously, I'd like you to take a look throughout the entire, solution, make sure that you understand it, kind of refresh in your memory what's going on. All right, but what I'd like you to do is justify why we can state this, why we can state this, and then finally why we can state this. Pause the video now and see if you can give reasons for each one of those particular lines. Well, this first line, right, is truly A equals B, right, then A times A equals B times B. And that, right, is the multiplication property of equality. All right, now, we kind of framed it when we were talking about solving square roots as, well, we're going to square both sides, right? That's kind of like how we justified it. Now really, to go from here down to this particular line, we really would be using properties of exponents and things like that, but I didn't ask you to justify this one. I did go down to this line and say, why can we justify subtracting an x minus 6 from, or subtracting an x and subtracting a 6 from both sides? Well, strangely enough, we would call that the addition property of equality, because we think about it not as subtraction so much, but as adding a negative x to both sides and adding a negative 6 to both sides. We have it all set equal to 0, we factor. By the way, even factoring itself can be justified using the distributive property, and then we set each factor equal to 0. Well, that is our favorite, the zero product law. All right. Now, the important thing is that every step in solving an equation can be justified with a property of real numbers or a property of equality, right? With the whole idea generally being, you can do anything that you want to an equation as long as you do the same thing to both sides of the equation, or if you're only manipulating one side of the equation, you're doing it with properties of real numbers. Now, right, let's take a look at exercise number 2. Check each of the values of x from exercise number 1. Show your check. Which root is extraneous? Does the extraneous root satisfy the equation x squared equals x plus 6? So let's talk about this a little bit before you dive in. right? Here's my original equation, and my two solutions were x equals 3 and x equals negative 2. What I'd like you to do is check both of those by hand. Don't use store in your calculator, but check both of those by hand in this equation. One of them is going to be extraneous, and one of them is truly a solution to the equation. Then, the one that is extraneous, I'd like you to check it in this equation. Now, you might be saying to yourself, why that equation? Well, if you look carefully, right, that particular equation is this one right here, right? And we kind of think about each equation that we get when we manipulate something in a solution as being algebraically equivalent to the one previous to it. So one would think that if an extraneous solution, or a solution is extraneous to this, it should also be extraneous to that one. Anyhow, what I'd like you to first do, right, is figure out which of the two solutions is extraneous by checking both of them, and then see if the extraneous one checks in this particular equation. Pause the video now and take a few minutes to do that. All right, let's do it. First thing I've got to do is just change my pen because I know that it is the wrong line thickness. Let me go back into my video, right? And now let's do the check. Here we go. So first thing I'll do is I'll check x equals 3 in my original equation, right? Simple enough. 3 is equal to the square root of 3 plus 6. 3 is equal to the square root of 9. And 3 is equal to 3. So that is a solution, which pretty much tells me the other one's going to be extraneous, given that I told you one was going to be extraneous. So now I've got negative 2 is equal to the square root of negative 2 plus 6. Negative 2 is equal to the square root of 4, and negative 2 is equal to 2. No. So that is extraneous. All right. Now, I promise you right now, x equals 3 will check in that. In fact, we could do a really quick check, right? 3 squared is 9, and then 3 plus 6 is also 9. So 3 certainly does check in this equation. But let's also take a look at this x equals negative 2, but in this particular equation, all right? So this is a completely different check. So negative 2 squared is equal to negative 2 plus 6. 4 is equal to 4. So yes. And therein lies the problem, right? Negative 2 is a solution to this particular equation, but it's not a solution to that equation. Now, notice, right, that what's going on here is that here, right, it's not a solution because negative 2 doesn't equal 2. And yet, if I squared both sides of this particular inequality, right, negative 2 is not equal to 2, if I squared both sides of that, I'd have 4 is equal to 4. Okay? So what's going on here is that squaring, when we square a number, we lose information, right? We lose whether or not the original number was positive or negative. So if I said to you, hey, I'm thinking about a number in my head, I square it, and the result is 16. What number was I thinking about? Well, you wouldn't know whether the number was 4 or negative 4, right? Squaring is irreversible. So once we square something, like we do right here in this step, we produce an equation that's got one solution that does solve this and one solution that doesn't. All right, let's explore that a little bit more in an additional problem. Extraneous solutions. The extraneous root in the last exercise gets introduced because the operation of squaring is irreversible, meaning that once we have squared a number, we cannot know the original quantity. All right, and again, there's many things that are reversible. Like for instance, multiplication is reversible. If I said, hey, I have a number in my head, I multiply it by 2, and the result is 30, what number did I have? Well, you'd say 15. There is no other number that when I multiply by 2, I get 30. All right. But as I pointed out before, right, squaring doesn't work that way. And let's look at an exercise, right, that really hammers that home. Exercise number 3. Consider the relatively easy equation 2x equals negative 6. Letter A. Multiplication is reversible, generally speaking. Solve this equation by reversing the multiplication by 2. All right, this should be super duper simple. This is an equation you could have solved either in 6th or 7th grade. Pause the video now and figure out what the one and only solution to this particular equation is. Well, I hope you got -3, right? So, in other words, if I take 2x and I make it -6, the common way of solving this is to divide both sides by 2 because it is the inverse of multiplication, and I get x is equal to -3. Now keep in mind we do that because we've been taught that that's what we should do in order to get x by itself. But the bigger picture in algebra is that we've been taught, hey, I can do anything I want to an equation as long as I do the same thing. So for instance, before we even get into letter B, right? You could say, well, instead of dividing both sides by 2, I'm gonna meander my way to get x equals -3. Like, maybe what I'll do is I'll take 2x and I'll add 10 to both sides, right? Nothing says I can't do that. 2x plus 10 is equal to 4. And then maybe I would divide both sides by 2 at this point, and I'd get x plus 5 is equal to 2. And then maybe I'd subtract 5 from both sides, and I'd get x equals -3. Nobody says I have to solve for x in the most efficient way. But let's take a look at what happens when we actually do that irreversible process of squaring. Letter B. Solve this equation by first squaring both sides. What extraneous root has been introduced? So okay, even though in your wildest dreams you probably wouldn't want to solve this equation by squaring both sides first, nobody says you can't do that. So I'd like you to pause the video right now and solve this equation by squaring both sides first and then coming up with the solutions. All right, here we go, right? And again, you might say, well, why would I square both sides first? And my answer is, yeah, I totally agree. That would be weird. But just like in the previous thing that I showed, you'd also probably not add 10 to both sides first. So if I square both sides, I'll get 4x squared is equal to 36. This is now a quadratic, but I can isolate the x squared, so I'll get x squared is equal to 9. And now I'll take the square root of both sides, and I'll get x equals plus or minus 3, right? I'll get two solutions, positive and -3. Now clearly, right, x equals 3 doesn't solve this. X equals 3 is extraneous, right? And it's extraneous because as soon as I square both sides, when I'm here, 4x squared equals 36, I don't know whether the original equation was 2x equals -6 or 2x equals 6. Now I know, and you know, that this was the original equation. But the algebra doesn't particularly know at this stage whether you started with 2x equals 6 or 2x equals -6, and therefore it produces two valid solutions to this equation, but one of them is not valid to that equation. And that can really get lost in the mix when you're solving a square root equation, right, like this. It gets lost whether or not, you've started with a positive on the square root or a negative on the square root. Okay, let's keep going, and let's also talk about rational equations. In the case of solving square root equations, because we square both sides at some point to remove the radical, we sometimes introduce solutions that do not make our original equation true. Don't get me wrong, you can have two valid solutions to square root equations. You can even have just one solution to a square root of equation that's perfectly valid. Right? Let's investigate why this can happen sometimes also with rational equations. And we begin yet again with just wanting to justify the steps of a rational equation, and then we'll take a look at an extraneous root. Exercise number 4. Consider the rational equation x divided by x minus 1 equals 2x plus 6 divided by x plus 3. Justify each step of the solution to this equation by citing a property or some other reason. Some steps of algebra will have been omitted for the sake of space. Now, I do want to point out that when we solved this type of rational equation back, a couple lessons ago, all we did was cross multiply, but we didn't really ever talk about why cross multiplication works. So I'd like to just take a moment to talk about that, right? The second technique that we looked at was clearing the denominators. And when we did that, we cleared denominators by multiplying all the fractions by something that would cancel both denominators. Now, when looking at this particular equation, what will cancel an x minus 1 is an x minus 1, and what will cancel an x plus 3 is an x plus 3. So my first step here is to multiply both sides of the equation by x minus 1 times x plus 3. Now, what justifies being able to multiply both sides of the equation by the same quantity is the multiplication property of equality. But think about what happens in that situation, right? The x minus 1's cancel here, the x plus 3's cancel there, and we have x times x plus 3, which is what you get when you cross multiply in this direction, and x minus 1 times 2x plus 6, which is what you get when you cross multiply in that direction. So when you cross multiply, what you're really doing is you're multiplying both sides of an equation that looks like this by the product of the two denominators. All right, what I'd like you to do now is pause the video and see if you can justify these two lines as well. Well, I'm hoping that that was pretty easy given that it's exactly the same thing that we saw before, right? There's a lot of manipulation and a lot of justification that we could do when we multiply these things out, including the distributive property, combining like terms, things like that. But then when we subtract an x squared and a 3x from both sides, again, a little bit weird, but we are using the addition property of equality in that sense. And then when we get all the way down here and we've factored and we set each factor equal to 0, we are then using the zero product law. Okay? Again, the point being that we can justify every manipulation we do in an equation with either a property of equality or with a property of real numbers. Now, the two solutions we've gotten to this are x equals negative 3 and x equals positive 2. And just like before, one of those two solutions is extraneous. Let's take a look in exercise number 5. Which of these two solutions is extraneous? How can you tell? All right, what I'd like you to do now is pause the video, and you should be able to tell without doing a full-on check which one of these two is extraneous. All right, well, it happens to be x equals negative 3. That is the extraneous root. And it's the extraneous root because it makes this denominator equal to 0. And I should go on to say, therefore, making the right-hand side of the equation, love red coming out, undefined, right? We cannot have a true equation. We cannot have a solution to an equation that literally makes one side or both sides of the equation undefined, right? Truth for an equation can only be established when you have a number equal to a number, not a number equal to something that's undefined. And that's truly what you'd have in this case, right? Because if I put negative 3 on this side, I'd have negative 3 divided by negative 3 minus 1, which would be negative 3 over negative 4, which would be positive 3/4 equals undefined. That doesn't make any sense, right? So therefore, that is certainly an extraneous root. Now, why does that happen? All right, that's what we want to explore next. And I call this multiplying both sides by 0. The extraneous root is arising in the last exercise because multiplying both sides of an equation by expressions containing a variable, that's key, is irreversible. So you can multiply both sides of an equation by the number 5, or by the number 1/2, or by the number 10/11, that's fine. But when you multiply both sides of an equation by an expression that contains a variable, that's irreversible due to the fact that we could be multiplying both sides by 0, all right? And we'll talk about that a little bit more in a second. But let's investigate this by solving another simpler equation. Exercise number 6. Consider the very simple equation 5x equals 15, whose only solution is x equals 3. Solve this equation by first multiplying both sides of the equation by x minus 1. What extraneous root has been introduced? Now again, I get it. Why in the world would you solve this equation by multiplying both sides of it by x minus 1 rather than just dividing both sides by 5? And the answer is you wouldn't, because it would take way more time. But yet, right, in our previous problem, we multiplied both sides of the equation by not one binomial, but by two binomials, both of which involved an x, right? And we could do that because the multiplication property of equality says we can, right? And so the multiplication property of equality also says I can multiply both sides of this equation by x minus 1. So I'd like you to pause the video right now, do that, you're going to get a quadratic, something with an x squared in it, and solve it all the way through. And you're going to get two solutions now, one of which will obviously be extraneous. All right, let's do it. So here we go. We've got 5x equals 15. Now I'll do 5x times x minus 1 is equal to 15 times x minus 1. I'll distribute here, and I'll get 5x squared minus 5x equals, distribute here, 15x minus 15. All right, now since I've got an x squared, I think I'll use the zero product law. So I will subtract a 15x from both sides and add 15 to both sides. I'm going to take that up here. I've now got 5x squared minus 20x plus 15 is equal to 0. Note that all the coefficients in that particular equation are divisible by 5. So I think I'm going to just divide a 5 out so that my life is easier. That's going to give me x squared minus 4x plus 3 is equal to 0. I'll now factor. Two numbers that have a product of positive 3 and a sum of negative 4 are x minus 1, or negative 1 and negative 3. So I'll get x minus 1 is equal to 0, x is equal to 1, and x minus 3 is 0, and x is equal to 3. Now remember, I'm solving this equation. 5 times a number equals 15. I'm going to go out on a limb and say x equals 3 is perfectly good because 5 times 3 is equal to 15. But 5 times 1 is equal to 5, right? So let's just be very clear about this, right? If I were to, for some crazy reason, actually write out a check here, 5 times 1 equals 15, 5 doesn't equal 15. So x equals 1. X is extraneous. And we know it's extraneous because, quite frankly, we knew from the get-go that the only root that was valid was x equals 3. So why is x equals 1 suddenly getting introduced as an extraneous root? Well, if you look at our initial manipulation, right, we had 5x is equal to 15, and I multiply both sides by x minus 1. Well, x equals 3 is still going to check perfectly fine in here, all right? So this is sort of line 1, if you will, line 2 in our solution. X equals 3 works perfectly good in that, and I could check that out, right? But if I put x equals 1 into this particular equation, I'd have 5 times 1 times 1 minus 1 equals 15 times 1 minus 1. That gives me 5 times 1 times 0 equals 15 times 0, and that's 0 equals 0. So x equals 1 checks perfectly well in this particular equation, but it doesn't check in the original equation. And really, what's happening here is I'm multiplying by the number 0 on both sides. And that is a very strange thing, right? Because you can have a patently false statement, right? 3 doesn't equal 4, right? Now, if I multiply 3 doesn't equal 4 by 2 on both sides, I get 6 doesn't equal 8. If I have 3 doesn't equal 4 and I multiply by negative 2 on both sides, I get negative 6 doesn't equal negative 8. But if I have 3 doesn't equal 4 on both sides and then I multiply by 0 on both sides, right? Now I've got 0 equals 0. All right, so What introduces extraneous roots sometimes when solving rational equations, equations that have fractions in them, is that when I multiply both sides by a quantity involving a variable, then I'm really multiplying both sides by the number 0. And that is an irreversible operation, just like squaring both sides. All right, let's wrap this up. So today we had sort of two purposes. One purpose was to take a look at why and what the reasons were for each step in solving a square root equation and solving a rational equation. And mostly that boils down to the multiplication property of equality, the addition property of equality, and the zero product law. But we also wanted to explore why sometimes when solving these two types of equations, extraneous roots arose. In the case of solving a square root equation, they sometimes arise because squaring the two sides is an irreversible process, right? And we kind of like played around with that with an example where you would never square in order to solve, and yet it still introduced an extraneous root. On the other hand, with rational equations, equations that involve fractions, right? The problem there is when we multiply both sides of the equation to remove the denominators, we have to do so by multiplying both sides by an expression that involves a variable. And because that expression could equal 0, depending on the value of the variable, if that particular value becomes a solution to the new equation, then it is itself extraneous. All right, I know that's a little bit deep, but hopefully it gets to why these extraneous solutions sometimes pop up, even though you've done everything correct in order to solve an equation. Okay, so I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.